Hello, I'm Ezra. This is AP Calculus ABBC Review, Unit 4, Conceptual Applications of Derivatives. In this unit, we go over rates in context, particle motion, related rates and optimization, tangent line approximation, and L'Hopital's rule. So, let's get into it. So, rates. What are rates? So, if you were given a function, let's say you have a lemonade stand and you earn money from a business. So, let's just say 5t. T is the amount of days in your business. And what this would indicate, let's just say this is M of t, the money you make. Every day, you're earning $5 more than before. So, on day 0, you haven't done anything in the business yet. So you earn $0. On day 1, you earn 5. On day 2, you earn 10, so on and so forth. And now, every day, you earn $5 more than before. So you can say the rate at which you're earning money from day to day is $5 per day. So, if you were to take this function 5t and you want to say you earn $5 a day, well, the rate at which you earn money is the derivative. So m prime of t, the derivative, is 5, which makes sense. Every day you earn $5 more than the last day. So the rate at which you earn money is 5. You earn 5 and then you earn 10 and then you earn 15. Now let's say you have water in a tank and it is filling up. I'm going to make a table for this because this is very common to see on the test. And usually they're pretty big tables. So, these are going to be in days, right? Or I'll say minutes, not days. So, each minute in this problem, hypothetical problem, you're filling up a tank with water. So, on day 0, you have 10 liters of water in the tank. Sorry, minute 0. You start out with 10 liters of water in the tank. A minute after, now you have 16. And then a minute after that, suddenly you have 26. And then a minute after that, you're going to have 40. And then a minute after that, you have 66. This is just some arbitrary table. So now, what could you say about the rate at which the water in the tank is increasing? Well, from here, you can't really get anything from the table. You know how much water is in each day. And if you wanted to find the average rate of change across the 4 minutes, I keep saying days, the 4 minutes, you could just do the average rate of change. However, if you want to find the rate at, let's say, minute 2, you have to approximate it with f prime of x, or if it were water, w prime of x, whatever function it gives you. So, how do you approximate? We're going to just say f prime of 2. Well, since you don't have a function, but you have values, you do the average rate of change over this interval. That's would be your approximation of f prime of 2. It's not an exact value, but it's pretty good because you have the change over this interval. So, 40 minus 16 over 3 minus 1 is going to give you 24 over 2, which is 12. And the units of this, think about it, we have liters, and every minute it is getting filled up. So the rate at which it is changing is liters per minute. Now let's say you have this same table, but instead of liters, you have liters per minute. So this is now the rate at which the water is filling up. So that means at t equals 1, after 1 minute, the tank is filling up at a rate of 16 liters per minute. So if we were asked the same thing, f prime of 2, then you would get same thing. I'm not going to do the math again, but you would get 12. But what's the unit now? Well, it's the same thing, except you have liters per minute, and then on the bottom, you're taking the rate of liters per minute. So you have liters per minute squared, because it's liters per minute per minute. Either of these, if you wrote it on the AP test, would be correct. I just prefer liters per minute squared. So, the units of any given table or function, when you take the derivative over and over, if you have the units of your x and the units of your y, if you take the derivative, it's just the units of your y over the units of your x. So if x is in hours and y is in feet, then your derivative is feet per hour. If y is feet per hour, then you have feet per hour, which is feet per hour squared. Now, speaking of feet or distance, we can look at a distance function. So let's say you have Jessica, who's running at a rate of 5e to the negative 0.1 t plus 3. So this is her position, I'm going to say. So at t equals 0, her position is at 8. She starts at 8. At t equals 10, her position is going to be probably around 5. And then at 20, it's going to be around 3 point something-ish. So how do we connect what we know before to this function? Now, we're going to say t is in seconds. This would be a very, very weird runner. But t is going to be in seconds, and then x of t is going to be meters. So, if you took x prime of t, the derivative of x of t, I mean, we can look at the function, but the function is not that relevant as compared to the idea, which is now, what would the units of x prime of t be? Well, meters per second, as we know from before. But meters per second is the unit of velocity. So that means that the derivative of position is just velocity. Now we take this one step further. This is our x prime of t function, but now knowing what we know, and of course I can't erase that. Knowing what we know, this is our velocity function. Now let's take the derivative again. V prime of t is 0.05 whatever, right? And now we have meters per second because our time t is still in seconds, so we just divide by seconds again, which is meters per second squared, which coincidentally is acceleration. So we have this really nice relationship between position, velocity, and acceleration. X prime of t equals velocity. X double prime of t equals v prime of t, which equals acceleration. So this principle is what defines particle motion in calculus. So we can do a sample problem. Take the function of, let's just say, a particle, right? Usually it will be a particle because humans don't move in a function like x cubed minus 7x squared plus 3. So let's say the position of a particle on the x-axis is this function. Find the acceleration at 2. Well, let's take the derivative twice, because we know acceleration is the double derivative. Let's take the first derivative. Let's take the second derivative. Okay. And then we set at t equals 2. What is the acceleration? Well, plug the 2 into here, and then we get a of 2 equals 6 times 2 minus 14. You can do the math on that. Negative 2, which would be our answer. And usually the problems do not get that much complicated than that. There is one more piece of information, which is how the AP test defines speed. Now, speed and velocity are almost the same thing. However, speed can only be increasing when acceleration and velocity have the same signs. Position does not matter here. So, sometimes it will ask you whether the particle speed is increasing or decreasing at t equals 2. What you have to do then is find the velocity at 2, find the acceleration at 2. It doesn't matter what numbers they are. If they have the same sign, then it is increasing in speed. So if they're both negative or if they're both positive, it's increasing. If they have different signs, so one's negative, one's positive, then the speed is decreasing. The position has no bearing on this again. Position has no bearing on whether or not the speed is increasing or decreasing. And when the particle is at rest, that means v of t equals 0. So that means it has no velocity. It can still be accelerating, but at that point, the velocity is 0. So, moving on from particle motion, we're going to talk about related rates and optimization, but related rates first. Now, this is one of the hardest topics in AB, and these questions usually take the longest. So what a related rate is taking a function entirely with respect to time. So I'll give an example right now. If we take the Pythagorean theorem, let's say that this is just some triangle, z, x, and y. What related rates is saying is that the sides of these triangles are changing in size with respect to time. So, if you remember implicit differentiation, how you take the derivative of something with respect to a different variable, that is similar to how we do it here. So let's say we take the derivative of x squared plus y squared equals z squared with respect to time. It's going to be the same concept, except instead of adding a dy dx for this, we're going to add a dx over dt for x, a dy over dt for y, and a dz over dt for z. Whatever variable it is, whether it be a, b, c, d, e, f, g, whatever letter, it will just be d, that letter, over dt. That's what you always have to tack on. So, in a problem using a Pythagorean triangle, it will say something along the lines of this. If x is equal to 3 and y is equal to 4, it will give you certain numbers. And essentially, once you derive the derivative, you can plug those numbers in and use algebraic manipulation to find your answer. So I'll explain what that means. If a problem tells you, in a right angle triangle, x is 3, y is 4, dx dt is -2, and dy dt is 1, find dz dt. That's a lot of information. So in a related rates problem, you want to write out the givens. So what did I just give? X equals 3, y equals 4. dx over dt equals -2, dy over dt equals 1. So now, we want to algebraically manipulate for dz over dt. So, here, we already have it kind of isolated. We just need to move this dz dt over to this side by dividing. So we have 2x dx dt plus 2y dy dt over 2z. This all equals dz over dt. Can we plug in our variables just yet? Almost, but we don't have z. So is this problem unsolvable? No. We have to remember that we have a Pythagorean theorem, and that if x is 3 and y is 4, then you can solve for z, and that's a 3, 4, 5 triangle, and then z ends up being 5. So now, we can plug in these variables. dz dt equals 2, 3 times -2 plus 2 times 4 times 1 over 2 times 5. And this is going to end up giving us -4 over 10, I believe. But what does this mean? We haven't really given a meaning to any of these. So let's explain what it would mean conceptually. So these numbers, I think, should be pretty easy to get. X is 3, y is 4, z is 5. That's just the lengths of the triangles. Nothing special there. dx dt and dy dt and dz dt are the rates that the sides are changing. So in this hypothetical triangle, somebody is shrinking the x side at a rate of -2 whatever time they give you. It could be seconds, milliseconds, hours, minutes, whatever time they give you. It's shrinking at a rate of -2, meters per second, we can just say. dy dt, by contrast, is growing by 1 meter per second. And now, knowing that relationship, you want to find out how much dz, or just z, is growing by. That's what dz dt is. How much is z changing with respect to time? That means, in this case, it is shrinking by -2 meters per second. This, if you think about it, makes sense that it would be decreasing, because in this equation, x and y have equal bearing, essentially. X is weighted no more than y. If x changes up by 2 and y changes down by 2, there will be no change. Here, dx dt is -2 and dy dt is 1. That means x is getting smaller faster than y is getting bigger. Since they have equal bearings on this triangle, it makes sense that z overall would be getting smaller because x is bigger than y. If they were equal, if dx dt was -2 and dy dt was 1, or -2 as well, or +2 even, the triangle would not be changing. So, let's move on to another example. Here, we're going to have a circle. Alright? Excuse my circle, but we're going to say at whatever time this is, it has a radius of 20 feet. Now, we're going to say that the radius is increasing at 50 feet per minute. We're giving these numbers now. Or units, I should say. Now, if I asked you to find dA over dt, then you could probably do it by just taking, let's say a is 2 pi r squared, right? How would you take the derivative of this? dA over dt equals 4 pi r dr over dt. Now, if you want to find the area, then you can just plug in your r of 20 and plug in your dr dt is 50. And then you'll get your answer, which is a very big pi value. It's going to be something along the lines of 4,000 pi, maybe, if I'm doing my mental math correctly. Or 8,000, something. But if I, for instance, didn't give you dr dt, instead, I said dc dt was 36 feet per minute. This is circumference. So now how would you find dA over dt? Well, you don't have this yet. So what you need to do is find what dc over dt equals. So we know the circumference is 2 pi r. dc over dt is therefore 2 pi dr over dt. And now we can isolate for dr dt, we can say dc over dt over 2 pi equals dr over dt. And then now we know what dc over dt is. It's 36. You plug this into here, you get 18 over pi, which is the same thing as 36 over 2 pi. And then now you can take this value and plug it into here alongside your radius, and then it will give you your answer. This is a very common problem on the AP. It very often won't give you a straight, easy one like the Pythagorean theorem where you can just plug in numbers. There will usually be some sort of initial step you need to take to find a missing variable, and then you can go ahead and turn around and just plug it in to your main equation. We're going to do one last related rate, which is another even more common one. We're going to have a cone. And then this cone is going to have a height of 12 and a radius of 4. There is water in this cone, and it is emptying out at a rate of -3 liters per minute. And this is 12 meters, I should put. So, if I wanted you to find the change in height of the water when the height of the water is at 4 meters, how would you do it? So, on questions like this, you will very often be given the formula. V is 1/3 pi r squared h. You do not need to memorize this formula. This is the volume of a cone. So, let's do what we did before. Let's take dv over dt equals, now careful, this here is the product rule. So, I'm going to split up 1/3 pi, and then we have r squared h. How would we take the derivative of that? Derivative of first times the second. So 2r dr over dth plus derivative of the second times the first, which is just going to be r squared dh over dt. Okay, let's look at this. We have our height, which is 4. We have our radius, which is... No, we don't. We don't have our radius. We don't know what our radius is changing by. So how can we isolate for dh over dt without knowing anything about our radius at height equals 4? So this is what we have to do instead. The height and radius in a cone are proportional. This is information that you must know for the test. So, the height here is 12, the radius is 4. That means the height here at 4, the radius is going to be 1. Maybe 4 over 3. Not sure if I'm doing my math right, but the height is just 3 times the radius, essentially. So, yeah, it will be 4 over 3, the radius here. So that means we can just move some stuff around. Then the radius is going to be h over 3. And this will make our equation a lot easier to handle. So, let's write our volume equation again. 1/3 pi r squared, so we're going to have h over 3 squared, because this is r squared. We just plug this into the r, times h, which is going to give us 1/3 pi h squared over 9h, which we can simplify, multiply everything out, h cubed over 27 times pi. So now, if we take the derivative of this, dv over dt equals, okay, derivative of h cubed is going to be 3h squared, so 3 over 27, I'm going to add the pi over here, h squared times your dh over dt. Now we're going to cross some things out. 3 over 27 is 1 over 9. So here we can just have pi over 9. H squared is our height, which is 4 squared. So 4 squared is 16. So 16 pi over 9. I'm just plugging in the variables we have now. dv over dt is negative 3 liters per minute. So, negative 3. And now, we just divide both sides by this, so we can isolate our dh over dt. And now, we can say our dh over dt is this very long and weird number, but that is correct. So, when it comes to related rates, you need to identify which numbers you have, which constants you have. Drawing a picture is very good for understanding the relationships between the rates. And you need to know if doing it one way is not going to net you the answer. You need to figure out that there's other ways to manipulate the variables to do things. In this case, knowing the height is proportional to the radius at any given point on a cone, you can come up with this relation right here, and that allows you to get the answer correct. Now we're going to move on to optimization, which I misspelled, but it's not as bad as related rates. So what optimization really is finding a maximum, minimum, however, closest, furthest, not furthest, closest, just an extreme for any sort of given scenario. So I'm going to first give a piece of information. So if you have a quadratic function like this, the maximum of this function will be this. And if you have a quadratic function like this, the minimum will be right here. So what's special about these points is, if you think about it, the derivative equals 0 up here because there's no slope. It hits like a sort of bump. So your derivative is 0 up here. And this is the principle that optimization relies on. So we can get started with a problem, and I'll explain more as we go. So this is a very standard problem. There's a river, and a farmer has 225 feet of fencing. This is going to be his fence. He only needs fence on 3 sides because there's a river on the 4th side. How can you maximize the area with that 225 feet of fence? So we first want to draw it out. Again, all these real world application problems, it's good to draw it out. Okay, so now we have this sort of rectangle here, and what we're going to do is label these sides X because they're going to be the same, and then label this side Y. Doesn't matter if you label this one Y and this one X, it's going to give you the same outcome. So now for every optimization problem, you are going to need to set up 2 equations. In this case, we will have an area equation, which is simple, x times y. And then we're going to have a perimeter equation, 2x plus y equals 225. Because 2x, which is this x and this x, plus the y, the lengths of all three of those will add up to the 225 feet of fencing. So now, if we have this function, I'm just going to denote it as a. If we have a equals xy as our area function. Now, how could we solve this? Because if we just take the derivative of it, it's not going to get us anywhere. So we actually need to manipulate this equation, which we have already a constant over here, and manipulate it to y equals 225 minus 2x. So these are, equivalent equations. But now we have a y equals something something x, and we can plug this into the y over here. And now we have a equals x times 225 minus 2x. This whole function is in terms of x. So we can multiply it out, which will make it easier to take the derivative of it. And then take the derivative with respect to x. Now, if you wanted, you could do 2x equals y 225 minus y, and then x equals 225 minus y over 2. And then you could take the derivative with respect to y if you wanted to. But that is a lot more work with all the fractions you have, and it's just not going to work out for the time that you have. It will get you the right answer, but it will take mad long. So the derivative is going to be pretty simple, 225 minus 4x. So now, using this principle, this is a negative parabola. It's going to look something like this. Doesn't really matter, right? But we know that the derivative equals 0 at this point, which is going to be when this area function, which we just derived, is going to hit its maximum. So the derivative will equal 0. We just set this derivative function equal to 0. Now you have 225 equals 4x, and that means 225 over 4 equals x, which is going to be, we can just leave it as a fraction if you wanted to. And that's probably going to be easier for this sake. So 225 over 4 is our x value. And now all we have to do is plug this right back into here. So final step, 2 times 225 over 4. You can cross these, and it's going to be 225 over 2. That's going to make it easier. Just cross out, simplify as you go along. 225 over 2 plus y equals 225. All right. So you could do the math here, or you can realize, wait a minute, 225, 1/2 times 225 plus another half times 225 is going to give you 225. So your y in this case ends up being 225 over 2. And those are actually your answers. X equals 225 over 2, or over 4. Y equals 225 over 2. And if it asks for the dimensions, that's your answer. And now it just takes one simple step. If it asks you for the maximum area, plug these in. Area equals 225 over 2 times 225 over 4. That's not a fun number, so I'm just going to write it as 225 squared over 8 and call it a day at that. If you had a calculator, you would need to simplify, plug it into the calculator. But that is that for that problem. These are sometimes usually more work than a related rate, but also easier, less confusing, and in the long run might take you less time because you can spend less time trying to figure out variables and things like that. So we're going to do the second type. I also have 3 problems for this. That was the first one. Here is another pretty common problem, and this is going to be the open-boxed or open-topped box aquarium with a square base. So whatever you want to call it. So if it wants you to minimize the surface area, the volume of this shape is 4, whatever units you want to use. And then we have to minimize the surface area. So here is usually the harder parts of an optimization problem, is picking your 2 equations. So we're going to keep this relationship back here. Alright, how would you get the surface area of this shape? It's open-topped, remember. This has stuff in it. This does, this does, this does, and the front does, but not the top. So let's think about the surface area. We have the bottom, which is just going to be x squared, because we have an x on this side, x on this side. The area of the bottom is going to be x squared. The area of this side, right here, is going to be xh. Same for this one, and this one, which is 4xh. Because, let me reiterate, you have the area of this bottom square, which is just the x times the x, and then the area of each of these 4 faces, because it doesn't have a top, each of the 4 faces is x times h. Okay. Now, again, you have your 2 variables, so taking the derivative of this would be useless. So how would we get either x out of there or h out of there? Well, we know volume is 4. But we also know the volume of a 3D shape is length times width times height. Height, not height. So we have volume is x times x, well, I'm just going to write it as x squared, times your height. Length times width times height. Alright, so we can just get rid of this v equals, because our volume is 4. So we're actually just going to have 4 equals x squared times h. And now it will be easier to get h out of this equation, because if you want to get x out, you get 4 over h equals x squared. Again, this is not wrong, but then now you're dealing with square roots. X is square root 4 over h. That is going to be extremely annoying to deal with, even more so than a bunch of fractions. So instead, we're going to do h equals 4 over x squared. So now, plugging this into here, our new relationship is s equals x squared plus 4x times 4 over x squared. Now this cancels this x out and this squared. These multiply together. So instead of writing this, we can just write 16 over x, because 4x times 4 over x squared equals 16 over x. That's where we got that from. So s prime is 2x plus, how'd you take the derivative of 16 over x? 16x to the negative 1, move it to the front. Negative 16x to the negative 1 minus 1, so negative 2. So instead of plus here, we're just going to have minus 16 over x squared. Set this equal to 0. Well, again, this is not really a parabola, but it's going to be the same concept because when you set it equal to 0, that's going to give you your minimum or maximum amount, but in this case, it's going to be your minimum. So you can have this as 0, so we have 0 equals 2x minus 16 over x squared, and then instead of writing that, we can move this minus 16 over x squared to this side, 16 over x squared. So, how are you going to solve for x? Well, times both sides by x squared. 16 equals 2x cubed. Divide both sides by 2. X cubed equals 8. And then now you just x squared, or x cubed equals 8, just means that x equals 2. So, all this math here, just to get that x equals 2. And now we have h equals 4 over x squared. X equals 2, so 4 over 2 squared equals 4 over 4, which is 1. So now we can just plug this back into here. And now we have the surface area equals 2 squared, so 4 plus 4, x, which is 2, h, which is 1, equals 4 plus 4 times 2, which is 8, so s equals 12. This is your minimized surface area. So again, all you do is you get your two equations. So you can substitute one equation into the other to make it possible to take the derivative of it with respect to x. And then you solve for x by setting your derivative equal to 0. And then, once you solve for x, you can plug that in to your original relationship, and then from there, figure out your final answer. Okay, we're almost out of the woods. Now we have just two pretty easy topics left. So, this is tangent line approximation. So, if you have a function, let's say x squared plus 2. Love using x squared. Or x squared, I guess not plus 2. You just have x squared. And then you wanted to find the tangent line approximation of 1.2 using the tangent line at x equals 1. How would you do it? Well, you have x equals y, x squared equals y. So, when x equals 1, 1 squared equals y. So y equals 1, and then that is the point at which our tangent line approximation will start from. So, to find a tangent line, you need, of course, the point, and then you need the slope. To find the slope, as you can imagine, you take the derivative. So y prime equals 2x. At x equals 1, that is going to be the slope for this function because this is the derivative. So at x equals 1, you have y prime equals 2. So the slope at x equals 1 is 2. So if we were to write our tangent line, we have y minus 1 equals 2 times x minus 1. So we have our full tangent line, and if we wanted to approximate x equals 1.2, we would then have to plug 1.2 in. So y minus 1 equals 2 times 1.2 minus 1. 1.2 minus 1 is 0.2. So I can erase this, just put 0.2. This still gets you full credit on the AP. And 2 times 0.2 is 0.4. So 2 times 0.2, I'm going to write it as 0.4. And now we just move this 1 to the other side by adding 1 to both sides. And now y equals 1.4. So, like the name suggests, this is a tangent line approximation. When you draw your tangent line at y equals 1, which is, I'm just going to say is right here. If you want to approximate 1.2, it's going to be close but a little bit off from that tangent line. So, how far off? Well, you can take your calculator and do 1.2 squared, and you're going to get 1.44. So, relatively speaking, it's not very far off. The closer you get to the origin of the tangent line on your approximation, the more accurate it will be. So for instance, if you were to approximate 1.1 or 1.05 or anything closer to 1 than 1.2, you would get a better estimate to the actual value than what we just got right here. However, the further you go away, as you would imagine, the worse the estimation gets. I'll show you. If we plug in x equals 2 as our approximative value, 2 minus 1 is 1. 2 times 1 is 2. Move the 1 over, y equals 3. Now if you plug 2 into the original function, 2 squared equals 4. So 3 is not a very good approximation of 4. And it gets even worse, exponentially worse, as you get further and further away from 1. We can try one more example. Let's take e to the x. And I'm going to say at x equals 1. So, at x equals 1, e to the 1 is e. So y equals e. And then dy over dx at x equals 1 of e to the x is e to the x. And e to the 1 is 1. So the slope is also going to be e. So our tangent line here is y minus e equals e times x minus 1. That is our tangent line at 1 right here. Okay, so if I wanted to approximate 1.1, I would do y minus e equals e times 0.1, because 1.1 minus 1 is 0.1. So, e on the left side, and then 0.1 e on the right side. You add e over here. Y equals 0.1 e plus e, which is going to be 1.1 e. Okay, now if you plug 1.1 into the original function, you get y equals e to the 1.1. And y equals e to the 1.1 equals 3.004, I think. Okay. Now what does 1.1 times e equal? Well, it's pretty close. 2.99. So, these two are extremely close to each other. However, if I wanted to approximate y equals e, or x equals e, I mean, or x equals 50, it would be incredibly off. 49e is so exponentially smaller than e to the 49th. So these are only for small distances away from the tangent line. Finally, we have everyone's favorite, L'Hopital's rule. Okay, so what is this saying? It's saying that you have a limit as x approaches a number of f of x over g of x equals 0 over 0, more commonly, or it can be infinity over infinity. Then you're allowed to say that this equals the limit as it approaches the constant of f prime of x over g prime of x. So don't get this twisted. This is not the quotient rule. This is you take the derivative of the top individually, and then you take the derivative of the bottom individually. So let's do an example, very common example. X approaches 0 of sine of x over x. First of all, in any FRQ problem where you must do this, you are required to show that it equals 0 over 0. In this case, it obviously does. Sine of 0 is 0, and then as x approaches 0 of x, that's 0. So here we're allowed to use L'Hopital's rule and say that this limit is equivalent to the limit as x approaches 0. This constant does not change. Of derivative of sine of x is cosine of x. Derivative of x is 1. So, since these are equal, we can say limit as x approaches 0. Cosine of 0 is 1. 1 over 1 equals 1. So you can say this equals to 1. However, you must again state that this equals 0 over 0 before you're allowed to say that it equals this limit. Requirement. This makes sense that it equals 1 though. If you look on a graph of the sine of x function, sine of x over x, it looks something like this, where this is y equals 1 at x equals 0. You can fact check this rule on your graphing calculator if you need. Here's another good one. Limit as x approaches 3 of ln of x over 3 divided by x squared minus 7x plus 12. Okay. Plug 3 in. We have ln of 1, which is 0, over 3 squared, 9, minus 21 plus 12, which is 0. ln of 1 is 0, and you have to say, you can't just say ln of 1, you have to say 0 over 0. Alright? Do not forget this. This is the most important thing that people very often forget, and I'm going to keep reiterating it. So, now we can say that the limit as x approaches 3 of the derivative of ln of x over 3 is just going to be 1 over x. We went over that in a previous video. Derivative of the bottom is 2x minus 7. Okay. Plug in 3. We have 1/3 over 2 times 6 minus 7. So over negative 1, which is just going to equal negative 1/3. Simple. Another just clean answer, but do not forget that it's 0 over 0. Now here is the last problem we're going to do today. x approaches infinity of x to the 10 over e to the 2x plus x. Okay, so I think it's pretty obvious here that it's going to be infinity over infinity, right? But it's not obvious to the graders. You have to state infinity over infinity, and then you can continue. So, limit as x approaches infinity of 10x to the 9 over 2e to the 2x plus 1. Wait a minute. This is still infinity over infinity. And this will keep being infinity over infinity. So, what do? Well, you could take the L'Hopital 11 times, right, to get rid of this. But if you think about it, 10x to the 9 goes to 90x to the 8, goes to 720x to the 7, so on and so forth. That will eventually hit 0, because it's a polynomial, which I've also discussed in a separate video. Every polynomial will go to 0 after infinite derivatives. However, e to the 2x, any exponential, is not going to go all the way to 0. They're going to keep the base. It's just going to be 4e to the 2x, 8e to the 2x, 16, infinitely. So eventually, let's say you take the derivative 10 or so times, right? You're going to have limit as x approaches infinity of 0 over 2 to the 10 e to the 2x. Alright, well this is 0. However, if you did it 9 times and got whatever millions constant, it's 10 factorial. That's the constant that's going to be on top. Over 2 to the 9 e to the 2x, something like that. Well, as this bottom one goes to infinity, this whole thing will go to 0. So, regardless, this will go to 0. So, you could L'Hopital it a lot of times, but recognizing this, on a multiple choice question, recognizing that this polynomial term will eventually go to 0, and this e to the 2x term will not, will save you so much time on any multiple choice. And it is very common. This is always tested at least once on the test. So, here are the takeaways for this. Know what rate means. Rate indicates derivative. Rates, if you keep taking the derivative, the actual units will just divide itself of the x term. So, meters per second squared, meters per second cubed, so on and so forth. For AB, particle motion is an important FRQ. So I'm going to star this one. There will always be an FRQ on rates. There will always be an FRQ on particle motion for AB. And knowing related rates and optimization is important. Even though only one of them only one of them gets tested on the test usually. So very often, they will not test both related rates and optimization. They will pick one of the two to give you. Whether or not it's on the FRQ or on an MCQ, they'll just pick one. And that's going to be the one that you're tested on. But know how to manipulate your variables for both related rates and optimization. Tangent lines. The approximation of tangent lines is all over the A/B test. BC, you need to know it because it transforms into something different for the BC test, which is talked about later. But knowing how to approximate tangent lines and taking your time, making sure that you don't mess up your arithmetic is very important. And finally, L'Hopital's rule is ubiquitous. Both AB and BC, there's always going to be one question that you need to use L'Hopital's rule for. So, know how to use it, and know if it's on an FRQ, you must indicate 0 over 0 or infinity over infinity. That's it for this unit. Thanks for watching.